Welcome everyone. And okay, with this big crowd, let's start with company update.
Uh, so yeah, normally I just talk here about how many tiny boxes we sold, and it's good. There's lots of tiny boxes sold. Um, the new $25,000 price seems to be good, so we will keep it for a bit longer before we raise it again to 29,000. Um, but yeah, no, longer term, like we're in a bad place right now with not having anything to submit to MLPerf. We need to get this Rangify stuff done, and we need to start having competitive memory usage and competitive runtimes with other frameworks. And I worry about. I've written a whole bunch of these abstractions. I wrote linearizer, um, now Rangify. I wrote the shape tracker. Like, I worry that if these abstractions aren't understandable by other people, then I'm not doing a good job. Then they're not good abstractions. Because the goal of code is not to be written or to be interpreted by machines, it's to be read. So if people can't read the code and understand what's going on, something's wrong and there's stuff that we have to change. Everyone here, at least everyone who works at the company, should be able to work on every piece of Tinygrad. At least to some extent. There shouldn't be any pieces that are like, oh, we can't touch that piece. And that's how I felt the scheduler. That's still how I feel the scheduler is. I don't know how to touch the code and grouper. Like the code and grouper that max one reduce op per kernel. Can only fuse assign if no other assigned target is used in the kernel. Can chase this down to contiguous children. Super confusing. And then that goes into a lot of other stuff that like pushes views around and well, all this is going to be going with Rangify, but it's important that we don't repeat the mistakes of last time and that this new code is actually understandable. So I'm going on vacation for the next 2 weeks, and I hope that everyone who works here and all the new people who are here right now can get Rangify merged without me. And I think that's a super important test because if that can't happen, then this is a bad abstraction and we have to go back to the drawing board.
Cool. I don't know. I think Grandify is easy to understand, but the implementation is hard to understand. That's my
The
impression.
implementation can definitely be worked on. The implementation is not the best code in Tinygrad yet. It was kind of my first pass at the implementation, but hopefully each part of it can be worked on individually too. Like the only part in Rangify that actually is interesting is part 3A. The part 3A lines 122 down to like 196. That's the definition of all of the movement ops. Part 3.5 is kind of interesting too. Part 3.5 is where we'll put in the cost functions. And even the very simple cost function that I wrote that just checks, that basically just says duplicate. Okay, so you get a choice many times between do you want to duplicate compute or do you want to store? So say you have say you have something that's reading from A and A times 2, right? And you have another kernel that's also reading from A times 2. Do you want to actually compute A times 2, or do you want both kernels to compute A times 2 locally? And this makes the trade-off to say that whenever it's an element-wise op, always just do it locally, whenever it does not expand. And that heuristic turns out to be a lot better than the heuristic that we had in the old scheduler. At least you can try right now, you can run Rangify, beautiful MNIST, and it uses a third of the memory and like 30% less kernels. It uses a lot more runtime though, but that's mostly just due to basically this stuff gets you FuseConf backwards for free, and those kernels are never fast. I'm not exactly sure why that is.
Uh-huh.
Um,
Can we briefly go through the Rangerify.py, and you can just say it out loud, like which part are hack, like ideally should be gone?
Sure. Okay. So the first part, part 0, do some cleanup rewrites, mostly copy from the old stuff. That's all hacks, and can all pretty much be deleted. You can see half of it's commented out.
Right?
That's mostly due to like bugs in the spec. I've already fixed the const thing. So like there was that const hacks, and then I fixed that in ops.
Okay,
You can
so
see there's actually an if range of it.
everything in part 0, if can be removed, we should remove it, is what you're saying?
Yes. Yes.
Okay.
Okay, then part 1. So I've drawn a distinction between contiguous and realize. So it's still called the pattern matcher is still called add contiguous, but should be called add realize. So contiguous is a user operation that says the user demands this be a buffer. Realize is a system operation that says, hey, I'm going to try to make this a buffer, but you're allowed to change that later if you want. Like you're allowed to optimize this buffer out. But yeah, so part 1 isn't really a hack. Part 1 is kind of just saying that, like, I mean, it's a hack, but it's a longer term hack. Saying things like, okay, copy, you have to realize the parents and children of copy.
Okay. So
Anything that's in the sync, you want to realize.
anything that's assign related issues, likely this part.
Anything that's assign related.
So there are several issues now with Rangerify assign.
Oh, I don't think those are in this part. I fixed most of them too, I think. At least, so the current assign and master is completely broken. The current assign and master, there's a test now that has an if rangeify in it because it'll only pass with rangeify. So I think the assign is, oh, you mean the assign in the diamond problem?
Yep.
Yeah, so the diamond problem is not caused by this. The diamond problem, this actually, you might be able to fix the diamond problem here. One solution to the diamond problem is to always make a copy before the assign and then remove the copy if you want to later. So like one way to always, like the problem with the diamond is when you have a kernel that's going to access both the assigned and unassigned version of a buffer. But
you
one
want
way to fix that is just always, yeah.
Okay.
I'm not sure exactly what the right fix is for that, but I don't think that's because of hacks here. Okay. So then part 2 is definitely not a hack. Part 2 just labels all of the children. Oh, well, okay. Lines 106 to 108 are a hack. I gate it so that not all children show up, but that can be removed now and can be cleaned up later. But the idea of going through the graph and figuring out where children are is not a hack and is a fundamental thing because you want to do things differently depending on.
What's the difference between ops child and ops children?
So ops children is the root node, and ops child is has things going off of it. So if you have like, let's say I have like a
The child is the
two
child of children.
a child is a child of children. Yes, yes.
Okay.
You kind of don't need the children op. I tried it without it. and just having the child ops on the other op, but there were some annoyances there. It was better to just have them both. So yeah, it has a little wider graph with a children and then as many childs as you want on the
Okay.
Yeah, so that's just does children extraction. That one's easy to see what it does in Viz. Okay, 3A, not many hacks in 3A. 3A is the replacement for the shape tracker. So this, in a lot of ways, is the definition of what all of the movement ops are. With a few more little cleanups there might be some subtle issues in that reshape function around symbolic. Whereas like symbolic has the stride of the max, but the shape of the thing. So yeah, there might be some subtle things in reshape with that. I think pad has been fixed up nicely to now use all the valid stuff. Hopefully it has. Yeah, I see ups and valid here. So that all should be pretty good. Span is pretty straightforward. It tracks these ending ranges that can maybe be deleted. And then shrink, permute, and flip are so simple that they can be written inline. Yeah. So these are like the definition of the movement ops now. Yeah, that's like going to exist, and then it runs through them. And then there's the other ops. When you're running rangifies through the other ops, that's what part 3B is. There's a lot of logic to deal with children here. So basically, if you have a node with two children, you look at the ranges in both the children. If the two sets of ranges in the children are identical, then you can ignore the fact that it has children. This will happen in things like ReLU, which has like a little cycle inside of it where you're doing this where and this max on the same input, and then combining them later. So then interesting thing. So if they totally don't match, if they have totally different sets of ranges, like that's what you'll see in like a long edge and a gradient, then you have to fully bufferize. You have to fully insert a buffer there. You have to realize everything at that point. But then with things like flash attention, you'll find that often they only mismatch on like one or two axes. And then you can create a buffer that doesn't take up the whole, that's not everything. A buffer that's only around for local context. So that's what that range of I equals 2 is. You can see on line 286, there's an assert range of I is greater than 1. So there's also some logic on 266 for that. So with range of I equals 1, it will either not insert a buffer or will insert a full buffer. And I think we don't have to get partial buffer stuff working yet. There's also some logic to handle partial buffer in map partial realize. But if you look at like map realize is probably a good function to understand like the core logic of rangeify. It's a 4-line function that just creates a whole new set of ranges, indexes based on those ranges, and then creates a buffer based on those ranges too. So you have like a buffer that's indexed based on a new set of ranges, and that's what it realizes. Yeah, so that's the logic in 3B. I wouldn't say there's so much hacks, but yeah, like once Rangeify 1 is stable and good, and we start moving into Rangeify 2, there'll be some changes made there. 3.5 is the cleanups. So 3.5, my strategy has been to overuse buffers earlier in the graph. Like anywhere you might want a buffer, just insert it. They're kind of painful to insert later. You can, but it's a lot easier to just remove them later. So yeah, insert extra buffers where you might want them.
Yeah, and that should not affect the correctness anyway, right? It's like the later removal ones are optional.
Yeah, so you can always remove a buffer. However, sometimes when you remove a buffer, you're doing an entire recomputation of that buffer.
Yeah.
So yeah, it's never wrong. You can actually remove all the buffers. At any point, you can remove every single intermediate buffer, and then you're going to get some horrendously slow kernel, which recomputes everything every time it needs it. Yeah, I think maybe I've shown off some kernels that look like that, where you can like put like an entire model in a. Yeah.
That was before you have some cost function to do some of these bufferize. Everything was super slow.
Well, before I had any cost function, what it was doing is it was creating lots and lots of buffers, which lots and lots of buffers can be slow, but it's fixed overhead slower. You can really see this with two gems. You can really see this with A, like A at B at C. So if you don't do any bufferizations of the intermediate, you end up with recomputing everything in the first matrix multiply n times. So you can do a full bufferize. You can like do A at B, store that in a buffer, and then do the thing stored at C, and that's a full like normally how you do two sequential gems. But you can also do a partial bufferize where you only store one row, and this is also correct. And there's like logic to do that. That's like the range of I equals 2 stuff, but we don't even need to get any of that stuff working yet. But that's the whole point of this, is to eventually enable things like that.
Cool. Let's continue with ranges of 4.
Yep. So part 4, put in buffers for bufferize. It converts the bufferize UOP into stores to actual buffers. It actually creates the buffer at this point. And then there's a bunch of logic for assign. Yeah, there's some hacks in there. Some stuff in there could kind of be changed, but the forced reshapes are there. I don't think we actually need those. And then so we'll get to that later. And then part 5 splits into kernels. So part 5 is pretty much the same logic as the old thing, which just says every store to global needs to be in its own kernel. I also added something this morning to renumber the ranges in the kernels, because all these ranges have global numbers. So in each kernel, I renumber them to be a local version of the number, and this allows the deduper to work. This also converts the buffers into defined globals. Yeah. And then the big function at the bottom, get rangeify map. So the old kernel eyes used to use this function called graph rewrite map. Graph rewrite map was a pain to understand. When things would break, you couldn't see it in Viz. There wasn't really a way to debug it. So I wrote it in a different style here. The first pass just goes through the tensor graph and assigns each UOP a number. And then you preserve these numbers all the way through. And then that way we know we have a way to correspond the UOPs in the big graph to the final buffers that are assigned to them. So you can see the logic on line 575 looks for all the buffers that are being created and says, okay, what numbers are the buffers being created on? Those are the ones that I'm going to put back in the big graph. Those are the ones that I'm going to those are the ones that I've actually realized and can safely put back in the big graph, so that they're the user doesn't have to recompute tons and tons of stuff.
In line 571, it says ranges with length 1 are handle, right?
Yeah, so if you use full symbolic, it converts ranges with length 1 into const 0. And there's just a bunch of things that expect a range, like the stores expect a range. That might be a simple fix. But range with length 1 is equivalent to const 0. But there's just some stuff not handling that correctly. And then the fix assign logic, I have not tested. I just copied that verbatim from the old one. I don't know if it's correct. And then in the end, we have this thing becomes map where we look for all tags on the sync, the tags on the sync that were assigned to in 577. And then put them in the becomes map, which is the graph, which is the map that's returned to tensor.py to actually convert the tensors into the UOPs. Remember, UOPs are immutable. So the only way that a buffer can actually become a real buffer is that the tensor, the pointer in the tensor, is replaced to point to the buffer instead of to the UOPs describing the compute.
So there are three UOP map here: kernel underscore assign, assign underscore rep, and becomes underscore map.
So kernel underscore assign and assign underscore rep. I think Rosalind wrote this stuff. I have no idea what it does. I just copied it verbatim. Well, I understand like what it does. I understand what the problem that this thing is fixing is. And we can get into what the problem is. But I don't understand how this I haven't like read this code and understand how it works. Becomes map is, I did write that. Becomes map is the single UOP to UOP map that says, here, you have this A plus B, and I've created a buffer on the output that actually contains A plus B. Cool, becomes map maps from the A plus B UOP into that buffer.
Okay.
So there should be one UOP dictionary. The other ones, hopefully we can figure it.
So every UOP should only be updated once. Like every time you change a value of become maps key. I mean, you shouldn't change the value of any key that's already existing in the map.
No, definitely not. Yeah. Those the key side of that becomes map, and we can document this better. The key side of that becomes map are UOPs that exist in the original big graph, and then the output UOPs are buffers and potentially some movement ops after the buffer.
Great.
Becomes map was the way we used to do this. Unfortunately, with graph rewrite map, it was really annoying to figure out like what should go in the becomes map. We had some logic to do that, but it had bugs. But now with the tag numbers, at least with the tag numbers, it's super easy to debug. You can just go in Viz and you can be like, oh, cool. Okay, great. That's tag 87. Also, like we don't have to like track this metadata through all this stuff anymore. You can see all the metadata stuff is just handled on line 531 in a one-liner. That just looks in the input list of UOPs and says, cool, UOP 27, great, you are a conv 2D, great, I'll put that in the metadata. Yeah, that's Rangeify.
We go through 3A again.
Sure. So 3A is the part that actually applies the movement ops to the ranges. So this was kind of the whole key insight of Rangeify. So Rangeify has two ops. Has one bufferize. Bufferize takes in a data and a set of ranges, and then it creates a buffer and stores the data at each one of those ranges. So if you want to create a buffer that's like the result of A plus B, and A plus B are tensors of size 10, you'll have A plus B as the first input into bufferize, and then the second input into bufferize will be that range 10. And that says create a buffer of size 10 and store all the outputs there. Then you'll also see in map realize that it creates an index with those ranges beforehand that tells you how to index into that buffer. That tells you where, given the range, you're going to find each thing that corresponds to that range. So when it's created, when it's realized, it's created contiguous in the same way we used to create shape trackers contiguous. But then these indexes work their way up the graph. They move to the left, and you apply the movement ops to the ranges. So like you can think like permute is very trivial, right? If I have something that takes in, range 0 and range 1, and then I have a permute on there where I like transpose the two, okay, cool. I just switch the position of the two ranges. Shrink, similarly simple. You just need to offset it if there's an offset, and that's really it. Otherwise, it doesn't matter. Flip, take the max, subtract it. Reshape is probably the most complicated. Reshape relies heavily on symbolic. It just basically creates the sum of all of them times the stride. So it creates like a real just single UOP with all the indices, and then it unpacks that using div and mod, and then hopefully symbolic resolves all of that to something nice, which it usually does. Yeah. So 3A is the you can see that each one of the things in PM mops on line 182 has a movement op followed by, that's what the .f is, an index. So there's an index on a movement op, and we're trying to return something that's just the index with the movement op applied to it, and it removes all the movement ops from the graph. That make sense?
Yeah, it's basically moving the movement ops again to the edges.
It's not moving the movement ops. It's actually there. Well, yes, sure, but they're disappearing. The movement ops aren't moving. They're embedded now in how that indexing works.
Yeah, they're sort of changing the index in place.
Yes. So if you step through it, you can really see it. The index like eats the movement ops and then updates itself based on whatever that movement op said to do.
Previously, these movement ops are tracked by like a shape tracker or a view that you start with a contiguous ones, then you ask, okay, after some kind of movement ops, what's the end value of the shape? Then go from there. In shape checker, you have the function to map that back to the index. And the problem is sometimes it's very hard to do that. And the changes in Rangify basically track all the movement ops and resolve it on the index level. And that's kind of a reason why invalid is very important here.
Yeah, invalid is definitely
the thing here
a
is
requirement
it
for
doesn't
this.
need to push the view. It doesn't rely on like resolving a very good shape checker. It's probably a similar math. I don't know. It should be.
It's similar math. Oh, by the way, a cool thing now. Remember, we used to have all that logic to handle all of the like pad. Can you push pads through this thing? Like, is this a safe op to push pads through? That's all fixed now. Wherever the pad op used to be, we just add a where.
But isn't the invalid
And then
of 0?
no, we add both. So if you read map pad, you'll see that both on line 162, we update the index to be invalid. But on line 164, we create a where with 0. And that where doesn't move. That where is now in the graph. So if you then upstream of that, to the left of that, do a something that's invalid, something that's would doesn't preserve 0, where f of 0 is not 0, this doesn't matter because that where will get rid of that later on. And we can do that because we actually have ranges at that point. It also keeps the invalid around, so it doesn't actually ever do the load from the bad part of the memory.
Yeah, but invalid always map to 0, no?
Well, yeah, but okay. So imagine, say you have something like a
So
load.
what happened if I have a tensor, I pad it, then I expand it?
Yeah. So the other way around. So that's not the bad one. The bad one is when you have a tensor, you say take the reciprocal of it and then you pad it. Right? If you have a tensor, you pad it, you take the exp of it, that obviously just works. But if you have a tensor where you tensor and then you take the exp or the reciprocal of it and then you pad it, this is where the old implementation would break and the new implementation is correct. Because it inserts a where after. Reciprocal is easier for me to think about. It's too late for me to think about what exp of 0 is. So it loads the 0.
Okay.
It does the reciprocal of 0, which is infinity. But then the where puts the pad back in and sets the value back to 0.
I thought we want infinity in this case.
No, we don't want infinity. So you want infinity if you did load, pad, reciprocal. Then you want infinity. But if you did load, reciprocal, pad, you don't want infinity. You want 0.
Okay, sure. Yeah. Okay.
And it's correct now because we insert the where in the two places. So we can remove all that logic where it's like not safe to push pads, gone. And then of course we can remove that second where later on. I think it's like he's already wrote the thing to do that. I might have been wrong that I think maybe it was only in range of 5, but he already fixed it, so that's great.
Okay. I think something's still wrong, but not very important. The save to pad is not for that case, but it's fine.
Oh, I think it is. I think you'll see the way the where is inserted, and you're like, oh, I don't care if things are safe to pad anymore.
Okay. Anyway, yeah.
Can you go through the children not making progress in search?
Yeah. So children not making progress. So I added a find that. So in order to, when you are when you're looking at the indexes of the children, you have to wait until both children are processed to the point that they have an index. So if you get to the first child and you haven't seen all the other children yet, you raise an exception called rewrite not ready. And rewrite not ready will say, okay, I'm not going to continue this path of the graph. I'm going to wait here until I see all the children. So children not making progress means that you've seen the node a ton of times. So basically just moves it to the end of the stack. So rewrite not ready says, you come back to me after you visited everything else in the stack. Children not making progress means you've come back to me, in this case, 10,000 times, and I'm not seeing any more children. So something's probably gone wrong. It's kind of like infinite loop, yeah. So the comment says, wait here until we have seen all the children. But sometimes for some reason, so if you have 2 children, you need to wait for them to both get an index. But sometimes one child doesn't get an index for some reason. Like a UOP gets stuck somewhere or something gets rewritten, and then it never gets an index, and that's when it raises children not making progress.
It's a late infinite loop.
Similar to infinite loop, yeah. Yeah, we could actually probably make that logic a lot better. We could probably make it something like if you raise rewrite not ready, and you're the only thing on the stack, it just kind of says, well, sorry, I don't have anything else to process. And that'll at least get that failure to happen instantly.
Yeah, after that point, you basically don't have any new answers to give to that match function.
Yeah. I mean, with
Is
all
what you're
things, with all like the
yeah. You're just like reinserting yourself back to until like it hits that many times.
yeah. I think like also with like graph infinite loop, sometimes we can explicitly detect the infinite loop, and it'd be nice to have a better error message when we can. You can't always. I mean, you can if you use like there's algorithms to do it, but they're kind of complicated and slow. But some of them you can detect right away. And yeah, it'd be nice to have better errors about that. I can kind of go through what I think the bugs are. I have the bugs listed in scheduler under good isolated Rangerify bugs on master.
Is it correct to say Rangerify overall is slower? Because it has a lot of rewrites. The same tests on CPU Rangerify compared to the old stuff, it's slightly slower.
I would think that the kernel time dwarfs everything else there. I bet there's some just dumb patterns that we haven't taken out yet. Some dumb like it's like making extra copies or something. I don't think that actually running Rangerify should be faster than the shape tracker. Like the graph rewrites themselves should be faster.
Yeah, and I think a lot of kernels are faster. I mean, with Rangerify, it's faster. Like
Yeah. So what
argmax,
I've seen is it.
schedule kernel.
What I've seen is your average kernel is faster with Rangeify, but there's a few really bad outliers that are 10x slower. And I think this is just because no one's really looked at them. I think once we look at them, we can fix them. And this is always, we would always say it's a comma, like a lot of effort has been put into the old stack. So like a lot of just manpower has been put into smoothing all the bugs over in the old stack. If we move to this new stuff, okay, well, there's going to be new bugs. And it's going to take that time, but hopefully less time.
Yeah. How does Rangerify work with image dtype?
It should happen all before that. I haven't tested it, but I would expect that all the Rangeify stuff happens before the image dtype. Like the image dtype's there, but it's just kind of ignored. I think it all just works.
Yeah, because it raised a lot of your verification fail on ops ptr cat. Also, what is ops.ptr cat?
Okay, so ptr cat is pointer cat. It's used in the devectorizer for basically saying like, okay, so say I want to load a float 4, right? So in order to load a float 4 on a GPU, the 4 floats need to be in order in memory, right? They need to have offset 0, 1, 2, and 3. But pointer cat is a way that you can express that when it's not that. Pointer cat says, I want you to load 4, and I'm going to give you 4 pointers.
So basically mstack?
Yes, similar-ish to mstack, yeah.
Okay.
Running Oh, GPU equals 1 doesn't work anymore. It's CL equals 1.
Yes, please. And now you can see why Karma really wants depth equal.
Yeah. Okay, yeah, it looks. Oh, yeah, image is failing with pointer cats. Yeah. Yeah, I don't know what that is. Oh, that might be because the store is broken. That might be
Yes.
because the
So
logic in this. Yeah,
there are some other tests basically saying your store has completely wrong shape.
my store is completely what?
The shape of the store is wrong, or the shape of a copy is wrong. Something very fundamental, not even for compute.
I say, yeah, no, I think that in order to fix images, I think the logic in bufferized to store needs to be updated. So also the JIT. So the JIT right now, there's definitely bugs in the JIT interacting with Rangeify. The JIT right now is using shape trackers, and that's going to have to be fixed. Like the JIT has this expected stvar as D-type device that's checking to make sure the input shape tracker is matching, and I think that's what's not working.
Okay. Not entirely sure.
I mean, it might also be just worth thinking about like how we can rewrite the JIT in a more modern way. The JIT's really old code. I bet there's some stuff that's just like a lot simpler to do now with UOps.
Okay. I think most of the kernel count looks good. I mean, the value is smaller. So
Yeah, there's a few that are bigger, and I'd be curious to look at those ones, but most of them are smaller, and it's pretty obvious why.
I think some of it is just the don't realize expand and stuff.
No, there's like some of it is just so dumb is because you're reshaping a buffer and you're putting it contiguous. Old scheduler would make that the same buffer. The new one doesn't. It says that contiguous creates a new buffer always.
Oh, we can fix that. Oh, we should fix that actually. That's a good bug to fix. Like, if it's literally just a reshape, then contiguous should be ignored. Because a reshape is the same buffer.
It is the
If
same
it's a
buffer.
permute,
Yeah.
you want the contiguous to work. But yeah, the reshape is actually the same memory. So like,
Yeah, you have to like pass over the tags and merge the tags.
yeah, I mean that
That's
should all. I supported. It should support tuple tags now, which are pretty nice. You can assign multiple ops to one in the new graph.
Okay. What are all the need a renderer arrow?
Oh, those are
Oh,
this tensor. This tensor is horrible to understand. I never got it right, even in the old scheduler. Barely.
yeah, I think now we can start removing hacks from disk tensor. And I'm thinking that Nimmelgen and Woes Parrot, I'm thinking between the two of you, you guys should figure out who's going to fix disk tensor and who's going to fix the JIT.
I'll probably work on disk because I need that stuff to work for cloud file system.
Great. Yeah, I mean, there's hacks in tensor.py to deal with like disk assigns. That can probably be taken out. Yeah, and that actually probably makes sense. Nimmelgen, if you want to take a look at the JIT and figure out how to make the JIT good.
Yeah. Okay.
And then also with an eye to the JIT like being more unified with HCQ graph. We have this abstraction now. The thing that I eventually imagine is that like you're going to have kernels in the big graph, and it's literally just going to be a bunch of rewrite rules to transform those kernels into the bytes that get shoved into the mech on the GPU. Right? Like this, like, you know, putting the drivers in Tinygrad kind of project. But yeah, no, I think you wrote the memory planner. I think the JIT is kind of similar stuff, figuring out how we could not use shape tracker in there, and yeah.
So the 3-fire Ulong is no longer web GPU complaining about a lot of Ulong stuff.
Oh, is that good or bad?
Oh, because web GPU doesn't support Ulong, which is using 3-fire, and previously it was resolved like in some rewrites.
Yeah, it should be rewritten. That should still kind of work.
That's fine. I think that's simple.
Seeds, maybe you want to take this one?
Sorry, what exactly was the problem with web GPU or refry?
So web GPU doesn't support uint64, but
Yeah.
3-fire algorithm use uint64. So previously, there's a rewrite kind of split one uint64 into two uint32, which supports by web GPU. But now I think because either the order is different or the old rewrite was not triggered, we just need to add it back probably, then it will work.
Okay. Yeah. I mean, I might have broken something with the index d-type lowering because that changed a lot of long.
Oh, I doubt you broke it. I doubt you broke it. I mean, I'm sure it still works on not rangeify. The rule was kind of fragile to begin with, but yeah, I think it's kind of, you've been working in that space. And then also for symbolic reshape, it's clear to me like reshaping from sims to ints and ints to sims never made any sense. The rule for reshape is that the product of both the like input shape and the new shape need to be equal. And you can't have a symbolic in one and not a symbolic in the other.
Yeah, that was rely on another hack in shape checker to something along the line with if input is contiguous, then just output the shape or something.
Yeah. I'm so glad all those hacks are going away. The new stuff should actually just, hopefully all the new stuff should be able to symbolic like pre-fail for LLMs and stuff.
Okay.
Yeah. I mean, I was working on the shape and using shrink.
Great. Yeah, no, I like what you said. I like what you said about you can only shrink afterward to smaller than the bound value. I think that makes a lot of sense.
I mean, you can actually, like with normal tensors, if you try and, well, with shrink it doesn't work, but if you try and use the like the dot get item, and you use a larger value, it just maximum. That's how like NumPy works as well.
Wait, it does what?
So if you have a symbolic shape which is bound to 4, and you do like get item with dot dot and then 100, so you try and slice 100 elements, it just gives you a tensor that has 4 elements.
Oh, there's 4 elements. Oh, I see. Yeah. Yeah, I don't know. I think we should explicitly assert if we can. But the other thing, if you're interested in this project, we should move the arguments. And this is this is a bit of a Viz thing too, because I want to keep it looking nice. We should move the arguments of reshape, expand, pad, and shrink as sources to the movement ops. So we have this problem right now where we have, if there's symbolic, there's uops in the argument, and there should never ever be uops in the argument. So yeah, we should move those to the sources. But I want to like keep it looking nice while we do this. I don't want it to start rendering, stuff all over the place. For permute and flip, these ones are okay to keep in the arg because the directive to permute and flip can't be a UOP. They kind of like control what the thing does, not like it's not an actual. It doesn't go in the shape. But yeah, does this make sense? Like the idea of like putting the reshape args as inputs.
Yeah,
Cool.
that should be doable.
What's the downside of UOPs in the arc? Like, I think we got away with it.
Oh, barely. Okay, so there's two big problems with UOPs in the arg. So one is they're not deduped. I mean, they're deduped at the global level, but they're not deduped at the graph level. So like, if you have like they don't point to the same place. They're not children. They kind of just don't exist. The it's like the other thing is like the it shouldn't come from nowhere, right? If you have a reshape that has the symbolic argument already in it, then your symbolic argument is in your graph. And like all the normal tools will show it to you. Tablasort will show it to you. S-parents will show it to you. Versus if it's in the arg, you have to explicitly look inside of reshapes, expands, pads, and shrinks in order to see if they have variables. And we have like a bunch of things that actually do this. And it'd just be so much easier to just do a Tablasort and look for to find vars.
Yeah, that makes sense.
I mean, I think it's the same with like the special arc where it's like,
Yeah.
it's fine. It's sort of nice in some way, but when you want to simplify,
Yeah, you can't do any processing on it. Yeah, we definitely don't want those in the args. Yeah, so those I'm not sure I have anything else to say about the bugs. I think they're all pretty clear. At least how to trigger them.
Okay. Everything.
I gave a bit of a timeline back in the scheduler. So I think by the end of Hong Kong, maybe even before it, if you guys can make great progress in these 2 weeks, then we can get it done before that. We can get all the old stuff removed. And what I consider this whole project kind of being on track is if by the end of the year we have state-of-the-art flash attention for MI350X.
I think the main problem
How
is
we-
we still don't know how to do the online softmax tile thing.
Yes, we
And
don't. Yes,
buffering thing. I think it's those two.
which thing?
Double buffering for Gen.
Oh no, do double buffering. Double buffering is easy.
Yeah, I mean sure, but we don't have it yet.
No, we don't have it, but the double buffering, I see very clearly what the transformation is using the stuff here. I wrote some demos of it in the AMD UOP MatMul stuff. That one I see. The online softmax I don't understand enough yet to say. So you're right, we don't have that yet. But we could have small flash attention that fits in the SMAM without the online. I didn't even know about that. The example I was reading, they had like a simple flash attention that didn't have that. But I don't know. I still think it's doable by the end of the year.
Yeah.
I mean, even if we don't totally have that, we have to have memory under control. Like we have to be able to train with these big context things.
Yes.
It does seem like Rangeify uses a lot less memory, and at least like with that stuff in 3.5, we can control the heuristic and figure out. I mean, you could write a heuristic in 3.5 that'll effectively do gradient checkpointing. Gradient checkpointing. Like imagine having those things tagged as long edges, and then long edge has like a big cost, and yeah, it'll checkpoint kind of automatically.
Yeah, I mean, if your children are kind of independent, then just do that. I think it's probably good enough.
Yeah. But yeah, I mean, it should be easy to play with these things now that are just always correct.
Great. Anything else or any questions for the people who are in this meeting? I still don't know why we add everyone, but since we add everyone, you can have questions.
I think it's a good meeting to add everyone for. I think we have to bet the project basically on Rangeify. Like this has to work.
Yeah, I mean,
It works. I know it works. It just takes time. In fact, it was
Well-
interesting seeing the criticisms.
what criticism?
Oh, yeah. One guy wrote like, "This just looked like a Walmart tier polyhedral compiler," and I'm like, "Okay, yeah, what's wrong with a polyhedral compiler?" And then the complaints about polyhedral compilers are that they're too flexible,
Yeah, I think we
and
don't
that
need
they.
a lot of polyhedral. My understanding, at least for the LLVM1, is they do a lot of things for like for loop or anything that can cause Turing complete some branches.
They do. The Halide shows some like good examples where they show like how they like split compute, how they like choose to like recompute sub ranges. You kind of need it for the DSP stuff. But for the GPU stuff, for like fast gems on GPUs and for flash attention on GPUs, you don't need it. Just normal rectangular tiling works fine.
Okay. Yeah.
Oh, how do you want to implement the backward and flash attention? There are some math tricks there. That's a question. Have not looked yet. Hopefully they're like the Sigmoid math tricks.
Let's get the forward first, and hopefully the backward
Yeah,
will automatically be good.
Yeah, that sounds good. Oh, we are going to have to stack the. We either are going to have to, in order to get backwards to D1 kernel, we're either going to have to stack QKV or we're going to have to support multi-output. I don't think multi-output's that hard though.
Yeah, we definitely want multi-output.
Well, so multi-output. Yeah, okay. Multi-output involves something that we haven't done yet. It's not that it's not doable, but multi-output requires you to like share ranges with children. Like you have to like merge the ranges downstream. Or we could have something where you specify like 3 things are like an output group, and then that's really easy. So maybe we'll start with something like that. Like in order for things to be multi-output, they have to have the same shape.
Yeah, sure. You can start with that.
Yeah. And then like that's kind of hard to discover. I don't know. It's not that hard. I mean, it should be pretty easy. It should be pretty easy.
Yeah, this is similar. Okay, not very important now, but doesn't sound very difficult. Okay,
Yeah.
anything else? What was the part that you struggled the most or spend like wasted most of the time on?
I mean, I had to get the whole other. I got all the post-op stuff in before this stuff had any hope of doing anything. So I had to move the whole optimizer from before Rangeify to after Rangeify. And I don't know, I kind of just like I had a lot of dread about doing that. I kind of like half-assed did it a whole bunch of times, and then I don't know. One time I just said, "Okay, this is really my only priority. I just have to do this," and that's done. It seems to work. So
Oh, and do the A range thing first. It's very good. I was pretty happy.
oh yeah. Now we can do things like the A-range thing first. But yeah, no, it was just so annoying to like kernel.py. Getting rid of kernel.py was terrible. We use that class everywhere. The multi-month project of getting rid of kernel.py, but it's gone.
Great.
And like this new stuff that we're getting rid of, like kernel eyes and stuff, is much more modern code and is much more well factored than kernel.py ever was. So I think that was the most annoying part. I think the Rangeify stuff is actually a lot better. It's a lot better than like the kernel.py removal project. The old scheduler removal project is a lot better than the kernel.py removal project.
Okay, great.
Cool. See you guys in 2 weeks. Good luck.
We'll see you in Hong Kong.
Sounds good.
Bye. Thanks, everyone.
Bye.
Next week
See
we
you.
have a meeting at the same time. So see you next week.